Hi, my name is Zirui. In this video, I'll be presenting our work Bandit Submodular Maximization for multi-robot coordination in unpredictable and partially observable environments. In multi-robot coordination problems, such as environmental monitoring, target tracking, and visual mapping, the robots always need to coordinate their actions with one another to complete complex tasks. And three factors always make these tasks very challenging. The robot's actions can have information overlap, the prediction of the environment can be inaccurate a priori, and the environment may not be fully observable even in hindsight. Let's dive deep into a multi-target tracking scenario, where the drones would like to coordinate their actions to collaboratively cover as many moving targets as possible in their limited field of view. The first challenge here is that, for example, if this action 1 is selected, then the drones have a quite large information overlap, which makes some targets covered by multiple drones while leaving some other targets uncovered at all. To overcome this challenge, we desire the drones to coordinate to select actions like this action 2. Then, if the targets are actually quite adversarial, then their future motion may not be well predicted, so it's hard for the drones to evaluate the effect of all alternative actions a priori. Consequently, they have to select actions using some past information instead of future prediction. Finally, since the drone's field of view is limited, they may not be able to observe all the targets even after they've executed their actions, and this makes them unable to know exactly which action they should have selected instead. The challenges above are not addressed by the current popular coordination paradigm, which applies offline monotone submodular maximization assuming the future environment is known. And this actually means the future environment is assumed to be predictable and fully observable. Here, monotone non-decreasing means the more robots are deployed, the larger the utility will be, and submodular means the more robots are already deployed, the less is the marginal gain given by deploying one more robot. In this paper, we reformulate the problem for such submodular coordination tasks to account for the above challenges in unpredictable and partially observable environments. In our problem formulation, the robots don't know FT a priori, but after selecting actions, they can observe the effect of their actions, that is, the value of FT that the selected actions achieve, as described in the green box, which is the bandit feedback. Solving this problem is difficult since even when the future environment is fully known a priori, this problem is still NP-hard, and it's been proved that the best approximation ratio of a polynomial time algorithm is a half. The state-of-the-art of multi-robot coordination problems stands as follows. While all these works address coordination problems, they either assume the environment is predictable or they consider the tasks where the actions don't have information overlap, or even both. In this work, we propose an algorithm that addresses both aspects as well as the partial observability of the environment. Then, let's see how our algorithm works. Our algorithm BSG maintains a probability distribution PTI for every robot's alternative actions. At every time step t, first, every robot simultaneously executes an action that is sampled by an onboard bandit algorithm from the probability distribution PTI. This distribution is computed based on past rewards. Then, the robots sequentially receive the actions that are selected by all the previous robots in a predefined order. And after that, every robot sequentially transmits what it just received, as well as its own action to the next robot. And finally, each robot computes the reward of its selected action and feeds it into the onboard bandit algorithm to update the probability distribution PTI. After a sufficient number of time steps, all the actions will be sufficiently sampled for estimating the rewards. Now, let's check the performance guarantees of our proposed algorithm. At each time step, BSG requires each robot to perform only one function evaluation of FT and a sublinear number of additions and multiplications. And as long as the environment is not adaptive to the robot's action selection frequency, then BSG enables the selected actions to have a guaranteed asymptotically a half near optimal performance, which matches the classical sequential greedy algorithm assuming a predictable and fully observable environment. We validate our algorithm in a 2D target tracking problem, where the robots have a limited field of view and the target's future trajectories are unknown to the robots. In particular, the targets may be non-adversarial with predefined trajectories, or they may also be adversarial when they are adaptive to the robot's motion. We compare our algorithm to a benchmark algorithm SG heuristic, which is the sequential greedy, however based on the observed environment at time step t-1, since the environment at time t is unknown. The first result shows that a higher action selection frequency improves BSG's performance, enabling a near constant or even decreasing distance from the targets for frequencies of 50 Hz and higher. And compared to the benchmark, BSG is superior, being able to keep constant or near constant distances from the targets in all tested scenarios. The intuition behind this is that BSG looks many steps into the past to determine what would be a next best action, whereas the heuristic looks at only one step back. In all, we've proposed a coordination algorithm with bounded suboptimality guarantee, although the robot actions have information overlap and the environment can be unpredictable and partially observable. In the future, we would like to first reduce the resulting action switching frequency by involving a cost, then enable distributed communication with only neighboring robots, and finally, let the robots act less conservatively by leveraging external advice such as inaccurate predictions of the future environment.